I so I have a second screen here where I put all of your faces, and I encourage everyone that feel comfortable with to have their cameras on. If you haven't been to through an experience with online seminars, it can be uh, weird to feel that you're speaking by yourself for an hour. So yeah, at least I see your faces and I see if you're sleeping or not. So it gives me some, it helps me a little bit.
I cannot put up my my video.
Okay, so first of all, thank you very much for the invitation to speak in this 50th year anniversary of the grad program at the UFRJ. I I have very good memories of my time in Rio. So yeah, so it's really a privilege for me. I feel very happy to be able to see a lot of familiar faces and to speak to you today. So the idea is to talk about stable ergodicity in the next 3 days, and I'll talk about it in different settings. And today I'll try to be not technical at all, and it will be more like a storytelling type of exposition today. So my idea is to talk about the history of stable ergodicity, or some of the history, because it's a huge topic. I want to explain the Hop argument in the in the another setting, and also sketch the idea of the Hop argument in the partially hyperbolic setting, so that we talk about Pilk-Schub conjectures and to describe the state of the art of these conjectures. Okay. So yeah, so before jumping in talking about Anosov and his works, actually I wanted to talk about Stephen Smale first. And I was very interested. I thought it was very interesting to learn about the history until Anosov got to the problems he worked with regarding ergodicity. And it was very interesting to see how Rio de Janeiro especially played a role in this thing. So here's a picture of Stephen Smale. So to start with, I wanted to mention that before the 60s, the belief was that Morse Smale systems were typical among the dynamical systems, and that structurally stable systems were Morse Smale. And here's something you can, I won't give all these definitions, but something to keep in mind here is that Morse Smale systems, they have finitely many periodic points. And something to keep in mind about structure stability, we say that F is structurally stable if for any G sufficiently, let's say C1 close to F, you have a homeomorphism of your space such that up to a change of coordinates using this homeomorphism, both dynamics are the same. So the dynamics are conjugated. And this belief at the time was built upon some works of Andronov and Potriagin. So I highlighted Potriagin here because he'll have a special role in this story. And also some works of Peixoto in low dimension. So we're talking about like vector fields and surface and things like this. So this was the belief before the 60s that this type of systems were typical. But then in 1960, Ismail, and this is a story that people in Rio de Janeiro have heard a lot, that he was visiting IMPA, specifically he was visiting Elon and Mauricio Peixoto at IMPA, and he comes up with this idea of the horseshoe. And a very cool thing is one of the features of this horseshoe is that it gives an example of a structurally stable system, but with infinitely many periodic points. And this goes against the belief that they had before that Morse Smale systems should be the structurally stable ones. And I found very interesting to read about this because nowadays, as you do like as you take a dynamical systems course, we see these things, and sometimes we take it for granted, and we don't realize how much of impact this type of examples and results they had at the time. And that's actually what happened with Anozov that I'll talk about just in the next slide. So this happened in 1960. And in the next year, so Ismail, he's invited to speak at a conference. So the name of the conference this year is Symposium of Nonlinear Oscillations that happened in Kiev. So he was planning to go to Kiev first for this conference, and then he arranged to visit Novikov in Moscow. And during this trip, he meets Anozov, Dmitry Anozov. Okay. So keep in mind, at this moment, you have Potriagin, that was one of the authors of a work that kind of gives this belief about Morse-Mail systems. And then you have Smail visiting the Soviet Union at the time to talk about his work. So we go now to Anozov. So this is a picture of Anozov, Dmitry Anozov. And in 61, so 61 is the same year when Smail goes to the conference in Kiev, and then he goes to visit Novikov in Moscow. So at that time, Anozov, he was a student of Potriagin. And Potriagin is the guy that I mentioned before that had this work that kind of gave this belief about the Morse-Mail systems. So Anozov, he's familiar with Potriagin's work. He's familiar with this belief, with this conjecture, right? And what happens is he goes to this conference in Kiev, and in that conference he sees Ismail talking about the horseshoe. And I got this quote from a paper of Anozov where he explains the history about the hyperbolic revolution. I found this very interesting. So he says, so while standing in line to register as a participant and looking over the shoulders of the people in front of me, I began to examine the stacks of these brochures. I read the title of one of them, Stephen's Mail, a structurally stable differentiable homeomorphism with an infinite number of periodic points. At that moment, the world turned upside down for me and a new life began. So I found very dramatic this quote, but at the same time, as I try to picture myself in Anozov's shoes, you have this belief, you have this idea of Morse-Mail should be the thing, the typical thing. Structurally stable system should be Morse-Mail. He's familiar with this because of his advisor. And then he reads this title, and I can see how this can be shocking. And he describes in his paper, Anozov, that at that moment he pretty much changed everything he was doing because he got so interested in this subject, so interested in this topic. So this happened in the conference, but then Ismail, he also goes to Moscow to visit Novikov. Anozov, he's a student in Moscow, so he's also there. And he describes that Ismail, he met with mathematicians there several times, and in one of these times, he explained more about his work on the horseshoe. And among the mathematicians that were present, Anozov was there. And he describes that Ismail, at the moment, he left two conjectures at that time. So the two problems, and you may look at this nowadays and you may think, oh, this is something I learned like in class, or I can learn in a book, or something like this. But the hyperbolic theory was just beginning. So those were important questions. So a first question he leaves is that hyperbolic automorphisms of the torus are structurally stable. So for example, you may think of the matrix 2, 1, 1, 1. So this is a matrix in SL2Z. So in particular, it acts on the torus. So you may see the D field that it induces on the torus. And you may wonder if this is structurally stable. Another one was if the geodesic flow of compact surface with constant negative curvature, if this is also structurally stable. So Ismail leaves these two questions. Another, he describes what happens next is that he pretty much, he describes that he left everything else he was doing and he got obsessed with these questions. And in particular with question 2, he started to study this question and to work on it. And in less than a year later, he ends up proving conjecture 2, but he actually proves something more, and that became his PhD thesis. So in his PhD thesis, he proves conjecture 2, but he also proves that any volume preserving C2 flow close to the geodesic flow, it's ergodic. And here, to say a few words on the history, for the geodesic flow with constant negative curvature, the ergodicity for the Liouville measure was already known by two independent works of Hopf and Handlund in the 30s. And the thing is that Nosov is able to push, in particular, Hopf ideas to to allow perturbations of this flow. So this becomes his PhD thesis, and actually the paper where he proves this is, to be honest, I've never seen the paper because I only find versions of the paper in Russian, but it's a 200-page long paper, and it was only published a few years later after he completed his thesis. So this is the starting point for us in this story of stable ergodicity. So let me put this in a more abstract frame. The key condition is uniform hyperbolicity here, and so let me define it. So we say that a diffel is uniformly hyperbolic, and nowadays we call it Anosov as well because of the impact that Anosov's work had on this subject. If the tangent bundle of your manifold admits the composition into two subbundles, we put a ES and U, and the S is to say stable, U is to say unstable. And these bundles, they have the property that they are invariant under the action of the derivative. The ES direction contracts uniformly under the action of the derivative, and the EU direction expands uniformly. And a way to restate Anosov's theorem nowadays with this language, before that, a remark is that these bundles, they are integrable in the sense that there exist foliations tangent to them. So there exists a unique foliation, which I call the stable foliation, which is tangent to ES, and another foliation, which is tangent to U. Okay. And a way to restate Anosov's theorem, or what Anosov proved, is that if you have a uniformly hyperbolic diffel with regularity C2, then that preserves a volume measure. So you may think of this as Lebesgue. Then the system is ergodic. So now let me highlight here two words. So you have uniformly hyperbolic in one, and then you have C2 on the other one. So you have these two hypotheses, regularity, C2 regularity, and this property, uniform hyperbolicity. So it turns out that uniform hyperbolicity is a C1 open property, meaning if you have a uniformly hyperbolic diffel, any diffel sufficiently C1 close to that one, you can guarantee that it's also uniformly hyperbolic. So this property here is C1 open. And with this result in mind, what you can say is that if you have a diffel F here, you may fix uniformly hyperbolic, volume preserving. You may fix U as C1 neighborhood of F such that for any diffel G in U, but with regularity C2, this diffel will be uniformly hyperbolic because it's close to F in uniform hyperbolicity, C1 open. And it has regularity C2, so you have that is also ergodic. So you have that this ergodicity property then becomes something robust in a certain sense for this type of systems, meaning.
Can I ask a small question?
Yes.
You're starting with a measure preserving a Nosov, and you take a perturbation.
Yes.
But doesn't the perturbation doesn't preserve the same measure anymore?
No, yeah. What I'm saying here is if you look at the ones that preserve the volume.
So you're assuming volume preserving perturbation.
Yeah. Yeah.
Okay. And so that's fixed. Okay, thanks.
Okay. Yeah. So you look at the, yeah, thank you for the comment. So you look at the volume preserving perturbations with C2 regularity, and they are also ergodic. Okay. So this gives us an example of something that has this ergodicity property in some sense in a robust fashion, meaning every C2 diffel volume preserving sufficiently C1 close will also be ergodic. With this in mind, I want to give a definition. So we say that a diffeomorphism F. So here I'm saying I'm using this notation M here to say that it preserves the measure little m. So a C2 diffel that preserves the measure little m is CS is stably ergodic if there exists a CS neighborhood of U such that for any G in this neighborhood with regularity C2 and preserving volume, it's also ergodic. And here, there is this weird thing with this S. And the thing is that you may consider different topologies depending on the example on the problem. So for us, you may think of S as being equal to 1. Oops. S is 1 or 2. That's the main things we're going to look at in the next few days. But
if you drop the assumption that the neighborhood of measure preserving what you get, is there a definition if it's just C2 close, but nothing else?
It is possible to replace this definition if you allow non-conservative perturbations. If you think in terms of what are called physical measures,
right?
Meaning you don't preserve volume anymore, but you could have a measure that captures the behavior of a set of full volume anyway. And you can also talk about stable ergodicity in this sense, but usually it's a hard problem already to know if there exist physical measures and things like this. So we focus on the volume preserving setting.
Oh, thank you.
Okay.
So the physical analogy of this is that the surface is not, you cannot stretch it. It's like rigid. Like you can perturb it, like you can push it in a spot, but that will preserve the volume. In other words, you cannot stretch the surface and increase the volume. Is that the physical analogy behind such a system?
I guess one way you can think of this is that it prevents the existence of attractors and things like that contracts volume. Like, but yeah, so it just says that for me, I like to think of this as that it already gives me a good measure to do ergodic theory, which is the volume measure. But yeah, you can think of this as if your system, your measure is being preserved everywhere in your manifold. Okay. Okay, so you have this definition. And just to make a comment before I put the next part of the slide. So these two here, I'm gonna talk more about this in a little bit. So these two here comes from some technical reasons. And actually, it is an open question to know if there exists a uniformly hyperbolic system F with regularity C1 that preserves volume such that F is not ergodic. So actually, I wrote in this way, but we don't know if a lot of systems with C1 regularity, if they are ergodic or not. So the C2 regularity appears for technical reasons, and this is some big open question. Okay, so let me.
But I mean, your technical condition is C2 implies the foliations are absolutely continuous, right?
Yes, and yes.
And if you drop C1, then the game's wide
yeah.
open.
And I guess some of the belief is that you should be able, there should be examples that are not ergodic because of the existence of certain hyperbolic sets. There are examples of hyperbolic sets with C1 regularity with positive measure,
Measure.
but are not everything. But again, to embed this into a completely hyperbolic diffil, it's we don't know how to do it, but this is the technical reason for the, and actually you can drop this these two by one placeholder, and this should be enough as well. Okay. So before, just keep in mind, you have this Anosov's result from 67. It took many years to get another example of stably ergodic system. So this came in 1994 with this breakthrough of Grayson, Pugh, and Shub. And what they prove is that the time-on map of the geodesic flow of a compact surface with constant negative curvature is stably ergodic. So let me say a few words about this. Before, Anosov was looking at the geodesic flow as a flow, and the perturbations were flows close to the geodesic flow. Here, you're not looking at it as a flow, as an R action. You're looking at this as a Z action. You're fixing, for example, F to be the time-on map of this thing. Now, this is a diffil. And in the space of diffil, you try to see if ergodicity is a robust property. And then the things becomes harder because as a diffil, you don't have hyperbolicity anymore. Why is that? Because you have the flow direction, and in the flow direction, you act as an isometry. So you have stable and unstable directions, but then now you introduce this new direction, the flow direction, and as a diffil, you see as an isometry in this, and this makes things harder. You don't have full hyperbolicity. But it does, the system does have a different type of hyperbolicity, which is called partial hyperbolicity. So let me define. So we say that F is partially hyperbolic if you have a DF invariant decomposition of the tangent bundle. So you have ES, EC, and EU. And as the letters may suggest, the ES and the EU direction, they are hyperbolic, meaning ES contracts uniformly, EU expands uniformly under the action of the derivative. But now you have this center direction here. And the center direction, you don't know if it expands, you don't know if it contracts. It can have both behaviors, for example. But what you do know is the following. So here, let me just maybe right here, M of dfx is C. So this is the notation for conorm. So this means you look at the inverse of this thing, you take the norm, and then you take the inverse of this thing. So the second part, it says that for some Riemannian metric, okay, for some Riemannian metric, if you see some contraction in the center direction, the contraction you see in the stable direction is stronger. And if you see some expansion in the center direction, the expansion you see in the unstable direction is stronger. So this type of behavior, we say that the center direction is dominated by these two directions, meaning you don't know if it expands or contracts, but if you see contraction, it has to be weaker than the one you saw in the hyperbolic direction. And if you see an expansion, it has to be weaker than what you see in the unstable direction. And yeah, so this is the type of hyperbolicity that this example will have. Okay. So let me give you a few examples of partially hyperbolic systems. So the first one is Anosov systems. If you think of EC to be 0. So if you don't have center direction, you're just left with stable and unstable, and then you recover. This is an Anosov decomposition. So this is one example. Another one is if you take a hyperbolic system, you may look at a product type of system where you put the hyperbolic system times identity. So this acting, for example, in the three torus here. So again, here from this side you get hyperbolic part. From this side, it's identity. So but you're dominated by the other two directions. So this is a hyperbolic, partially hyperbolic system. Another one is, so this one might be harder to believe, but you look at this 4x4 matrix. So you may, if you're bored at this time of the talk, just compute the determinant of this matrix. There's a bunch of zeros, so you'll make your life easier. You may verify that this matrix belongs to SL4Z. So in particular, in this volume preserving action on T4, you may look at the detail that acts on T4 by this matrix. And it turns out that this matrix, it has one eigenvalue greater than one eigenvalue smaller than one, and then it has two eigenvalues with absolute value 1. So this means that the eigendirection corresponding to this unstable eigenvalue, it's going to become a hyperbolic direction for the action of this diffel. So you see uniform expansion. This one you see uniformly contraction, and the subspace that corresponds to these two complex eigenvalues with absolute value 1 is going to give you the center direction. So it turns out that this is a partially hyperbolic system with center direction, with the dimension of the center direction 2. So this is one example. Another one is Q products. I'm not going to define in a general frame, but for example, you can think of a system with x, y, z coordinates on the three torus. You let your 2, 1, 1, 1 map act on the first two coordinates. In the third coordinate, you put z, and you add some perturbation that depends on the other coordinate. So here I put sine of 2 pi x. It turns out that this system will be partially hyperbolic. The center direction will correspond to this direction of the fiber. Okay. And one last example to mention is the time-on map of the geodesic flow of a surface with constant negative curvature. So here you have a stable, unstable direction, and then the center direction comes from the flow, from the vector field direction, from the flow direction, which the action of the derivative in this case would be just 1, because it's an isometry along geodesics. Okay, so here are some examples. And something interesting in the history is, so you have this work of Grayson, Pugh, and Schutz. With the methods on their proof, they come up with a program and some conjectures. And I took this quote from one of their papers where they introduced their conjectures. And they state, so this is Pugh, Schutz. So they state that our main theme is a little hyperbolicity goes a long way in guaranteeing stable ergodic behavior. Okay. So with this in mind, they make this first conjecture, which is C1 stable ergodicity is CR dense among the volume preserving CR partially hyperbolic diffeels. Okay. And here, something I did not mention is that if you look at the set of partially hyperbolic systems, so of a manifold, this is open set, C1 open set. Okay. Partial hyperbolicity is a robust property. So their conjecture is that inside this world, stable ergodicity should be the typical behavior. Okay. So before stating, so they break this conjecture down into two other conjectures, but before stating the other two conjectures, let me just try to sketch a Hopf argument to give some ideas of what is the reason behind this conjecture. Okay, so our idea here, let me maybe write what is the setting we want to look at. Now, suppose you have a C2 volume preserving another diffil, and we want to prove that this system is ergodic. So a first key ingredient in this idea, so this actually, it's the idea of this argument goes back to Hopf. So this is called nowadays this is known as Hopf argument. So a first ingredient in the idea is to use Birkhoff's ergodic theorem. So some of the consequence of this theorem is that if you look at a continuous function of your manifold, you have a set of full measure, so a set depending on this function of full measure, with the following properties. For any point in the set, if you look at this function, which are called forward Birkhoff errors, so it's the limit of the average of your function phi along the orbit of x for your dynamics. So this thing is well defined. The backward Birkhoff average, so you do the same thing looking to past iterates. This is also well defined. And a third point is that those two values, they coincide for almost every point. Okay. And one of the consequences of Birkhoff's theorem is to say when something is ergodic. So something is ergodic, so our system is ergodic, if and only if, for any continuous function, and for almost every point, the forward Birkhoff average equals the integral of your function. Okay. So this can be very useful. This will be very useful for us, this type of idea. So we're trying to see that our Anosov diffil is ergodic. One way to think of this is to say, okay, if it's not ergodic, then there exists some continuous function, and you can find two measurable sets, capital X, capital Y, such that they have both positive measure. And you can also find some value alpha with the property that the Birkhoff average of phi for points in capital X are smaller than alpha, which is smaller than the Birkhoff average of phi for points in Y. So this just comes from the fact if your system is not ergodic, then you should have some function such that the forward Birkhoff average is not constant everywhere. So you can just separate them by some value alpha. And this sets, from what I'm calling this sets, capital X and capital Y. Okay, so so some people look at Hopf argument as being divided in two parts. So when you're doing this, when you look in this way, a first part comes from the following, we can call it lemma, but it could be thought even as some exercise for an ergodic theory, which is now we have this function phi, some continuous function, and we take a point in that set given by Birkhoff theorem, so lambda phi. So the first thing is to say that for every Q in the stable manifold of P, both forward Birkhoff average coincide, and for every Q in the unstable manifold of P, both backward Birkhoff average coincide. And here, this is an easy consequence of the following. Phi plus of P, it's well defined. So the limit exists. And this is the limit of 1 over n sum j equals 0 to n minus 1 of phi composed with fj p. The second thing is that since Q is in the stable manifold of P and phi is a continuous function, then if you look at phi of fjp minus phi of fjq, this goes to 0 as j goes to plus infinity. So you use those two things, then it's not hard to conclude this. And you apply similar idea for the past iterates using the fact that Q would be in the unstable manifold now. So this is one way to look at this statement. Another fancier way to look at this statement is to say that, so I'm just gonna write some words, but it's just to keep something in mind. It's to say that ergodic components of M are S and U saturated. And there, so here are some fancier words, but the thing is just that if you have some typical point for an ergodic component such that its peak of average sees that component, then points in the stable manifold and points in the unstable manifold of that point, points in the stable manifold will see the same average, and if you do the backward average, points in the unstable manifold will also see the same average. So this is one way to look at this part of the argument. Yeah, but for the moment, let's just keep this in mind. I don't know why I did twice this thing. Okay, so now let's see how to do Hopf argument. We can fix 2 points, x in capital X, so we can fix this to be a density point. And you can fix y in capital Y, also a density point of, so a density point of X, a density point of Y, a Lebesgue density point. So here you have X, here you have Y. Since you're in the Anosov setting, volume preserving, you can prove that the stable manifold of X intersects the unstable manifold of Y. So at a point Z here. Okay. So what you want to do is to play a game with the following set of equalities. So we know that phi plus of X. So on the one hand, this is smaller than alpha because of the definition of capital X. On the other hand, since Z it's in the stable manifold of X, we can say that these two things are equal. On the other hand, we have that phi plus of Y. So this is greater than alpha because Y is in the set capital Y. On the other hand, so if we choose Y to be a typical point as well, we can say that this equals phi minus of Z, phi minus of Y first, which equals phi minus of Z. And what we really want to do is to say that those two things are equal, that we can go from phi plus, from forward peak of average of Z to backward peak of average of Z. And if we could say this, then we'll get a contradiction and our system will have to be ergodic, because then you have alpha greater than alpha type of contradiction. So the idea is, how do we justify that we can choose Z to be in a set of full measure? And this is the key thing that Anosov proved. It's a property called absolute continuity. Absolute continuity. So what does this mean? So first of all, you may look at the stable foliation. And it turns out that the stable foliation usually is not super regular. So it's usually just Holder for typical Anosov systems. So they have smooth leaves, but they are holder in the transverse direction. But they still have some good regularity called absolute continuity. And the thing is that if you fix X and Y here in the same stable leaf, and if you fix two transversals to the stable foliation, T1 and T2, you may look up what's called the holonomy map between X and Y, which is the map that you take a point here, P, you look at the stable manifold, this piece of stable manifold, and you see where it intersects the other transversal. Okay, and absolutely continuity means that, if B is a set in T1, if you look at the measure in T1 of B, if this has zero measure, then if you look at the measure in T2 of the image by the stable holonomy of B, this also has zero measure. And one of the consequences of this is that if B has positive measure, then the image also will have positive measure. Okay, so this is the key thing that Anazov proved. And yeah, and this thing is so crucial for everything we talked about in stable ergodicity or in ergodicity for these systems, that, and it's the main place it's the only place in this proof at this moment where we use higher regularity. So in this case, C2, but this is also true for C1 plus holder regularity. Okay. So once you have this, so I will skip some of the details now. The idea is that you can find a typical point X and a typical point Y in those two sets, and in such a way that now this point Z belongs to lambda phi. And because of this, you have that phi plus of Z equals phi minus of Z, and that closes the sequence of equalities that I was writing, and this gives you some contradiction. Okay. Yeah, so there are a few ingredients that are important here for Hopf argument. In this picture, one is that you have transverse intersections between stable / unstable manifolds. You can also think of this as having a SU path, a path in stable and unstable manifolds connecting X and Y. And a third ingredient that we used was absolute continuity. Okay. All right, so let me state one. So there is a way also to generalize this idea for partially hyperbolic systems, and using a Hopf type of argument to talk about density points instead of looking at directed transverse intersections. But a key ingredient that appears in these things is something called accessibility. And accessibility means that for any 2 points in your manifold, you can connect those 2 points by a path that is contained in stable and unstable manifolds. So that means that if you only walk along stable and unstable manifolds, you can go everywhere in your manifold. So with this definition in mind, Pugh and Shoup, they broke their main conjecture into two. So our first one is conjecture 2 that I wrote here, is to say that stable accessibility is dense among partially hyperbolic diffeos. And a third conjecture is to say that accessibility implies ergodicity. So if you had these two things, if you had the knowledge of those two things, so if you know that accessibility is dense among partially hyperbolic systems, and that accessibility implies ergodicity, if you combine those two things, that implies that stable ergodicity is dense among your systems, among partially hyperbolic systems. So in what follows, I just compiled some of the state of the art regarding these conjectures. So here, conjecture 1 is completely solved when center dimension is 1. So that's a work of Hertzets Uris. When center dimension is 2, Hertzets Tazibi Uris, they prove the C1 version of this conjecture. So they prove C1 density of stable ergodicity. And this was generalized to any center dimension recently by Avila, Crozier, Wilson, where they prove C1 density of stable ergodicity among partially hyperbolic systems. Then for CR density, there are some partial works of Avila Viana, Orita Sambarino, where they prove CR density of stable ergodicity in certain classes of systems with center dimension 2. And with any center dimension, this was recently done by Legil and Zhang with more hypotheses, but again, it's for certain classes of partially hyperbolic systems, but they can also prove CR density of these things. So maybe I'll skip this conjecture. I want to go to this other one, and I'm running out of time. So you have this other conjecture about accessibility implies ergodicity. The best result we have so far is this work of Burns-Wilkinson, where they prove that accessibility plus a technical condition called center bunching implies ergodicity. And this is a non-trivial generalization of a previous work of Pugh and Shub, where they have an extra assumption. And you also have a work of Burns, Ogopiat, Pezin, where accessibility plus information on Lyapunov exponents, meaning negative center Lyapunov exponents, implies ergodicity. But so far for this conjecture, this is the best result we have so far. And in this next, just one remark is that all the works on stable ergodicity, they use some type of generalization of Hopf argument. And one thing that you see in the theory is that you have Hopf argument, and then you have pretty much two types of generalizations. One comes from the ideas of Pugh-Shub, Grayson Pugh-Shub, Burns-Wilkinson type of thing, where you have this technical condition called center bunching. And in this approach, so I'm writing here in quote marks is that you don't care about the center exponents. This is not completely true, but yeah, if as long as you have center bunching, you can forget about more detailed information of the center, and you can apply some generalization of Hopf argument done by them. Another type of approach, which is closer to the idea I gave of Hopf argument, comes from Pezin theory, where he extends Hopf argument to the non-uniformly hyperbolic setting. And a comment here is that the first approach has been used a lot more in the theory and when you try to approach these problems of stable ergodicity. And our idea in the next couple of days is to look more to this second type of approach using Pezin's theory.
So you don't assume anything about integrability of the center distribution, do you?
No.
I mean, one-dimensional, you've got it, but otherwise, no, right?
No, but even in one dimension, you don't necessarily have it. There are examples of headsets, UDIs, where you don't have integrability of the center, and the center is one dimension. And that was a big step between Pugh-Shub's result to Burns-Wilkinson, because the hypotheses are very close to each other, except that here they assume integrability of the center. And it was a non-trivial work to remove that hypothesis. Okay. So I wanted to point out those two approaches of, I mean, I didn't explain those two approaches, but you have those two types of approach of generalization of Hopf argument, one that appears in Pugh-Shub, Burns-Wilkinson, another one that is Pezin's theory type of approach. Just to say that we're going to explore more this second type of approach in the next couple of days. And I just wanted to finish to say a few words here. So tomorrow, we're going to investigate this Bejer-Carrasco example, again, using the approach of Pezin theory. And on the third day, we're going to explore when you're out of partially hyperbolic world. So that's something that we call weakly partially hyperbolic systems. So and again, using pacing type of techniques to understand this world. Okay, so I'll stop here. Thank you.
Okay, thanks. There's some question to Davi.
When you say Payson theory, you just mean the full Payson theory for the invariant measure? And you look at the Lyapunov spectrum of it?
Yeah, so pacing theory, I talk about, so Pacing's original work from like 77 or something, that you actually want to have a volume to be a hyperbolic measure. So you have all the exponents. And the other idea is that you want to find intersections between stable and unstable manifolds for Pacing manifolds for typical points. And if you can do this type of things, then Pacing in his paper already would imply that your measure will have to be ergodic.
Right.
But his paper is already a generalization of Hopf argument to non-uniform hyperbolic settings, where he proves that if volume is hyperbolic, then you can have at most countably many ergodic components. The way you conclude this is by saying that your ergodic components all have positive volume. And to conclude this, you use Hopf argument with Pezing's manifolds.
Okay. Anyone?
Davi, can you hear me?
Yeah.
Yes, we can.
So I have a question. Right in let's say, in the beginning of the presentation, we were discussing if a transformation in the neighborhood, let's say, of an Anosov map was going to preserve Lebesgue measure. And we discussed very briefly that they could have a physical measure, for example. In case they have such a measure, can we say that this physical measure is also ergodic?
So in the Anosov setting, if you start with an Anosov diffil, actually, yeah, any Anosov diffil with regularity C2, what you can prove is that there exists a unique measure mu, which is physical, and he has full basing. So for Anosov systems, you know about the existence of physical measure, but you require higher regularity. Okay. So no, hang on. Maybe I'm saying something. Maybe I don't know about uniqueness. Yeah, I'll say there exists for the moment. Yeah, so in this case you do know, but but we can talk about stable ergodicity for example, partially hyperbolic systems. For these ones, you don't know. If you go to non-conservative systems, you don't know about the existence of physical measures. For Anosov, it's okay. That's works of Sinai, well, and Bowen.
In case we know the existence of such a measure, that in the Anosov case, for example, let's stick to the Anosov case. So imagine we take another transformation nearby the Anosov transformation. Maybe it don't preserves Lebesgue, but it has a physical measure. Let's say it's unique to make it easier. But can we conclude the ergodicity property also transferred to this?
Yeah. So actually, if you add,
measure?
so I said something wrong here. This is not full basing, but if you add the hypothesis of transitivity, then the measure is unique and has full basing, and it is an ergodic measure in this case. It is an ergodic measure.
Sorry, but I think that what you can prove is that for every epsilon, so you have an open set of anodes such that the basing of this measure has volume 1 minus epsilon, and then you can guarantee that for C1 generic anodes, then it has full basing, I think, and then it's ergodic.
So what so if you take any another, but here I'm adding the hypothesis of transitivity. This gives you that the SRB measure will be unique.
Yeah. No,
And for
I
any
think so. I think that if you take one is that volume preserving, and then you perturb it, then you can find an open set of anodes such that that physical measure has the volume of the basing is 1 minus epsilon.
Yes, I think will be full basing because volume preserving will imply that the anodes is transitive, and that's robust.
Okay, I see. Okay.
And I think this implies full basing.
Okay, thank you. Someone else? Okay, let's thank Davi again.
Yeah, thank you.
Eveline,
Yes. So
it's your turn.
now
it's your turn.
actually it's Alexander. We wait 3 minutes for the next talk. I will make Daniel, I guess, co-host now.
Oh, Daniel.
I'll make you co-host, Daniel, just a second.
Okay.
But I don't find you. It's strange. I can see you, but I don't find you in the list of
I don't exist.
participants.
You're a ghost.
You are stronger. You are a stronger cat. I see you, but I don't see you in the list of participants.
It's a ghost account. Yeah, me here.
He's at the very top. He's right under the co-host.
He's already the co-host? No.
No, he's just by the co-host. He's next to Luciana.
Ah, yeah. Thank you.
Oh, yes. Yeah, thank you, Stephen.
He was hiding under.
Yes.
There he is.
Now I think you are able to.
Okay, let's try.
So, so we need 2 minutes before we started because I have to restart the YouTube.
Okay.
If you can wait 2 minutes. Alexander, you are in charge, actually.
Okay, no problem.
I'm going just to try to share to see if everything is okay.
Okay.
So can you see my screen, right?
Yes.
Okay. So I'm going to stop and start.
So let me just see if I can.
So YouTube is not working.
I think now it's moving to it. It was not working the last talk, but let's see. Let's cross. It's working. Now it's working. We are back.
Now we have Isaiah.
Yeah, we have the recording. Yeah. So we put there.
Yeah, we needed this kind of bump to be more feeling at Rio. If everything works smoothly, we feel like we are in any place, but we are not. Now, right now, we are in Rio, so it's more real. So we are. I'm ready when you want, Alexander.
Yeah.
Okay, then. So so it's a pleasure to me to introduce the next speaker, which is Daniel Ismanuel from ICMC and from São Paulo. And well, Ismanuel